Today we're going to review for the Chapter 7 and 8 practice tests. In Chapter 7 you looked at confidence intervals, and in Chapter 8 you looked at hypothesis testing. Most of the time you're able to choose between completing the problems using formulas and solving them algebraically by hand. Other times you may want to use the calculator. For mean, population proportion, and mean when you don't know sigma, you can use either method. But when you're looking for standard deviation or variance, so those confidence intervals are doing a hypothesis test for that, you'll need to do that by hand. We're going to go back and forth between the PDF, Smart Notebook, and the calculator. I'm going to rely pretty heavily on the calculator to try to keep the time down in the video. So if it can be done using the calculator, which 75% of the time it can, we're going to use the calculator, but I would recommend trying to complete the problems that you can use the calculator with by hand to see that if you understand the process and you can get those same numbers. So that way when you're working with standard deviation and you don't have the calculator to rely on, you can make sure that you kind of understand what the process looks like. Number 1, express the confidence interval negative 0.061 less than p and p less than 0.579 in the form p hat plus or minus e. So you got a couple of different ways you can express confidence intervals. We have the interval notation that we're looking at here. The calculator spits out something pretty similar to that you will use set notation, so it won't put the p-value in the middle. We're looking to put it in the form where we're going to be able to see the best point estimate, and that's the sample data. Here it's p hat, but it could also be x bar or s, plus or minus the e value. And it's pretty easy to do. If you're given the confidence interval, the only thing that you need to do to find p hat is take the mean of your high end and your low end. And then once you get that mean, subtract it from the high end. So 0.579 minus that mean, which is my best point estimate, in this case p hat, 259, and I'll get my error, 0.32. So 0.259 is p hat plus or minus the error of a 0.32. Number 2, 334 college students are randomly selected. It was found 103 own a car. Find a 99% confidence interval. All right, so as soon as you hear a confidence interval or test the claim, you want to start paying attention because it's going to tell you to what level that you want to know. So a 99%, a 95%. And it's going to tell you in the next part which confidence interval you want to find. In this case, we want to find the proportion of all college students who own a car. And so that's going to be a 1 prop z int, since I'm talking about intervals. To get to that, my calculator, I'll go to stat, over to test, and I'm going to scroll down till I see 1 prop z int because I'm looking for an interval. X is the number of people that give you the answer that you're looking to measure. In this case, we're looking to see how many own a car, so that's 103. N is the number of people that you spoke to, it's 334. That C level is your confidence level. And so all we need to do is change that 95 to a 99 and hit calculator. It pops out pretty fast. Let's go 3 decimal places, 243 and 373. 243 to 373. And that's my confidence interval at a 99% confidence. That was Holly. I think she's done now. Let's see, number 3. Newspaper article about the results of a poll says, in theory, the results of such a poll in 99 out of 100 cases, so we're talking about a 99% confidence interval, should differ by no more than 2 percentage points. And percentage points can be tricky. We'll talk about that in a second. In either direction from what would have been obtained by interviewing all the voters in the United States. So what a confidence interval is, or what it does, I guess it should say, is it takes your sample data and says, all right, this is just a well-selected sample. So we know that there's going to be outliers in both directions that maybe that we didn't get a chance to include in our data set. So if we were to poll everybody, the true population proportion would probably not be exactly what we got from the sample, but it would be somewhere in this particular range, and that range is what you find for the confidence interval. Since I want to find out how many people I need to speak to, and which is going to be how many people they spoke to in this particular study, I need to think about whether or not do I know p-hat. Did they say, hey, you did this sample and you found this percentage of people? No, not in this one. So this one I don't know p-hat. When I go to my formula sheet for sample size determination, I'm going to have to use the one that says p-hat unknown because I don't know what happened in the study. And so I'm looking at the critical z-value that corresponds with that alpha, or in this case the beta value, the confidence interval percentage, squared p-hat times q-hat. And if you don't know that, then you assume that it's a 0.5 in both, so we'll use the 0.25, over my e squared. So the number of people that I need to talk to is my critical z-value squared p-hat times q-hat, which we don't know, over the e squared. So if we don't know it, that's a 0.5 times a 0.5. That's where that 0.25 comes in. The critical z comes in from the confidence interval, and for a 99%, that's going to be a 2.575. Over my error squared, and what's a little tricky is that it's at 2 percentage points, so that's 2%. You cannot work with a percent, so we'll need to change it to a decimal, which is a 0.02. So I'm going to use my calculator to help me out with this. I have a 2.575 squared times 0.25 divided by a 0.02. That quantity squared, and I get 4144. Now with these, even though mathematically this rounds to a 0.0, right, so you'll have 4144, we always go up to the next whole person, so this is going to be 4145. So I need to talk to 4,145 people in order to always create a confidence interval that has an error of 2 percentage points. Now that doesn't mean that the range will always wind up giving you the same high end and low end. It just means that it will always be off by a 0.2. So your answer for that one is 4,145 people that we need to speak to. Do one of the following as needed. Find the critical z, find the critical t, and then state whether you're going to use the normal distribution, so the z's, or you're going to use the t. So I got a 99%. That's not terribly important as far as whether or not you're going to use a t or a z. That just tells you where to look on your chart. N is 17, so for the normal distributions, if something's normally distributed, we would just use a 17. If it's a DF situation, then it would be 16, and that's the number we would need to find our critical t. But this is the big important piece right here. Sigma is unknown. So if you do not know sigma, the best case scenario is that you can use a t. Best case, you can use a t. You can use a t if it appears to be normally distributed or really close to being normally distributed. In this case, it appears to be normally distributed, so I can use a t. Had this said skewed, we wouldn't have been able to use either. So to find my critical t value, I need to go back to that formula card and go all the way down to my critical t chart, which is right after my z-score chart. And I'm looking for the area in the two tails, which would be a 0.01 since I have a 99% confidence interval. Go down the degrees of freedom chart till you get to the 16, and then scoot over. So underneath the 0.01 is a 2.921. And that's the value that we're going to use as our critical value, since we have to use a t-score and not a z-score. 539 packages are randomly selected. They have a mean weight of 29.9 and a standard deviation of 3. What is the 99% confidence interval for the mean weight? So this is either a Z or a T. Now, when they gave me the standard deviation, they didn't say, hey, all of the things that you know about that get mailed through here that match this type of packaging have this kind of standard deviation. It didn't say anything about all of the values being equal to the 3, or you weighed all of them and found a population standard deviation. This is from the sample, so this is going to be an S. So I don't know the sigma value, so that means I have to use a T interval to generate that confidence interval. So back to the calculator, I go to stat, over to test, and I go down to T interval since we're looking for our confidence intervals. I have the actual statistics this time, so I'm going to scoot this over to stats and hit enter. X bar, I hit the wrong button. X bar is 29.9, standard deviation is 3. I had 39 packages and I want a 95, so I'm going to change that back to 95 and I hit calculate. It takes a little bit longer, but it will give you the confidence interval. It will also give you the X bar, which we already know, and the S of X again, which is nice if you have a situation that you are running it with the full data set and not the measures of center and variation already. And I say, let's say 28.9 to a 30.9. Same number of decimal places. Yep, so we're good. Find the minimum sample size needed to estimate an unknown population mean. So we're talking about mu again. And we want to know how many people do we need to speak to in order to create a 90% confidence interval that was based upon a data set that yielded an error because the confidence that had a sample mean within 2.8 pounds of the population mean. And the population standard deviation is known to be 27, and so that's sigma. So we're going to be able to use z-scores for this. If I go back to my formulas and table card, and I'm looking for a sample size determination, you see mean only has 1. My critical z times sigma over e, and then square all of that. So my critical z for a 90% is 1.645. My standard deviation for the population, they said, was 27, and then E was 2.8. So I'm going to need to find that value and then square it. 1.645 times 27 divided by 2.8 squared. 252, since you always go up to the next whole person. So even if this was 251.2, I would still say 252 people. That's how many people we'll need to speak to. 252. 30 randomly selected students took a calculus final. Sample mean was 75. The standard deviation was 13.2. This is for the sample. It does not say all of the calculus students in the world. So this has to be an S value, which means, again, we're talking about a T interval. Find a 99% confidence interval for the mean score. Back to the calculator. Stat, test, T interval. Again, I have my stats. X bar was a 75. S it was a 13.2. I had 30 students in my sample and I want a 99% confidence. So let's say calculate. And eventually we'll get a t-score. There we go. It doesn't say where to round, so let's go to one place past the decimal and say 68.4 up to an 81.6. You will have a z-interval on your test, and it will be pretty obvious because it will say something like all of the students that ever took the exam have a standard deviation of, or it will specifically say the population standard deviation is. And so you'll know that then it's got to be a z-interval. Given the degree of confidence in the sample data, find the confidence interval for the population standard deviation. So no calculator use on this one. That's not going to help. The mean replacement time for a sample of washer machines, 20 washer machines, so ends 20, gives a mean value of 9.4, although we're not terribly interested in that, and a standard deviation of a 2.5. Find a 99% confidence interval for the standard deviation sigma, not sigma squared, but just sigma of the replacement times of all the washer machines. So N is 20, that means DF is 19. And the values that you're going to use to generate the confidence interval, or chi values, they are not symmetric, although I always wind up drawing my little bump symmetric. However, the error in the tails will still be half on each side. So if I'm talking about 99 in, that's a 0.01 out, which means 0.005 on the left and 0.005 on the right. I'll need to find those cutoff values. They will not be opposites with the chi values. And on top of that, it runs differently than the other bars, other tables, in that you're going to look at area to the right. So I'm looking from here up, and I would cover, if I was going to paint all of the area to the right of here, that would be 0.995. So when I go to the table, which is the very last table in your fold-out card, I'm going to look at area to the right, 0.995, and I'm going to go down to 19 because that's how big my DF is, and I get 6.844. Now I'm going to do that same process, but I'm going to start at the other wall and say, all right, so from here up, it's just the 0.005. Still at the 19, but now I'm going to go to the 0.0051 and go all the way down to the 19, and I get 38,582. Now notice on your formula card, you do not get a confidence interval formula for standard deviation, but you do get one for variance. So what we're going to have to do is, after we find this, we're going to have to take the square root of everybody. I'm going to pull this formula over and put it in a smart notebook so we have some room to work. Notice that the left and right values swap. So the small number that's off to the left is actually going to come over here. That's 6.844. And then the 38 point something 8582-ish, that's going to be over here on the right. So n minus 1, that's DF, I know that's 19, times S, which was a 2.5, square that number. And then bring the right-hand value, the bigger value of 38.582, over here. That is the low end, almost the same on the other side, except my denominator is going to be that 6.844. And so I don't have to type these numbers in my calculator twice. I'm going to just take the square root right away. That way I'm really only going to be talking about sigma, which is all I really care about. That looks a little bit like an S, or now it looks like an upside down comma, and not variance. Calculator. 19 times 2.5 squared divided by 38.582 square root. So I'm going to hit second x squared. Second negative sign, so it says take the square root of the last answer, and I hit enter and I get a 1.8. Do the same thing on the high end. 19 times 2.5, 2.5, so I know that's still an 18.75. This time I'm going to divide by a 6.844. Again, I'll say second square root, second negative sign, so I take the square root of that big long 17.35 dot dot dot, and I get a 4.2. And that is your confidence intervals. So you're going to have 1 Z, 1 T, 1 population proportion, and then of course 1 for chi values. Now it's time to talk about some hypothesis testing. Test the given claim. Use the p-value or the traditional method. So p-value, you're probably going to be relying on the calculator, maybe for the whole process, maybe for just finding the area under the curve. Traditional method is using the critical z values. It doesn't matter to me really which one you use. But you will need to identify, and this is important, in order to get full credit, you need to tell me both the hypotheses, so H naught and H sub 1, the test statistic, and then either the critical value or the p-value, depending on what method, and then you must state the conclusion. We'll talk a little bit about what that conclusion is in a second. So I have a sample of 167 children. So that's my N. Randomly selected from one town. I found that 37 of them all suffer from asthma, better than what's going on in Huntersville, where lots of kids are suffering from a very rare eye cancer that somehow is plaguing the Huntersville area. Use a 0.05 significance level. That's your alpha, so that's the error in the tails. And we'll set up tail or slash tails in a second. We want to test the claim, and so your ears perk up, that the population proportion of all of the children in the town is 11%. So we think that all of the kids in this town that are suffering would generate a p-hat value of 11%. And so my claim is p is equal to 0.11. That's my claim. As soon as you say equal to, you know that that's the null. The alternate is the opposite of whatever the null is. So the opposite of equal to, which is my claim, is not equal to. This is the first part where you need to say the null and the alternate, and yes, you have to label them. Now I'm going to need a test stat, a p-value, and create my conclusion. Well, if I'm talking about an equal to, that's a two-tailed test. And if it's 0.05 out, half on each side, this is going to be a two-tailed test because of that equal sign in the middle there. This p equal to in my claim. And I want to find out what's the probability if I throw a dart at the map that I land in this area right here, wedged in between these two values. This doesn't want to let me shade, so you're just going to have to take my word for it. Oh, there we go. So I'm going to use my calculator for this. It's a population proportion, and it's a hypothesis test, so I'm going to go stat calc 1 prop z test. This p naught up here is the value from your h naught, 0.11. X is the number of people that gave you the answer yes to the question you're answering. So like, do you have asthma? Yes, that's 37 people. 167 people were asked. And then this next one, you're going to match the symbol in your alternate. I'm already set up on the not equal. Now you could say calculate or draw. Even though the draw is a little bit neater as far as the values that it spits out, you can't really see often the shading. So I'm going to use calculate. And there's my p-value. Be on the lookout for very small p-values. And there's my test stat. So my test stat is 4.61. Really big or really small, so bigger than 3.5 or less than a negative 3.5 is probably going to be a reject the null. But we got a p-value that we use a capital P for of not 4. You cannot have a p-value bigger than 1. It is about percent of area under the curve. You cannot have 400% of the curve. This is basically a 0 because it says take this decimal point and go back 6 spots. So this is 0.00005, also known as 0 for us, right? Because we usually go 4 decimal places. So now we have to test this claim so that we can come up with a conclusion. Is the p-value less than alpha? That's the question. P-value is a 0. Alpha is a 0.05. Yes. 0 is less than a 0.05. If your p is low, the null goes. So we are going to reject the null. What does that mean for our study? We're going to use probably the most useful part of this formula card, which is the hypothesis wording flowchart underneath p-values. Did the original claim contain the equality? Yes, because my claim was that it's going to be equal to 11%. So follow this top arrow right up here. Did you reject the null? Yes, I did. The p was low, no goals. There's sufficient evidence to warrant the rejection of the claim that the percentage of children suffering from asthma in this town is 11%. I am fine with you stopping at this spot right there. But we are going to just take this whole piece and put that in here. Maybe not. So we'll have to just type it out. Reject the null. There is sufficient sample evidence to warrant the rejection of the claim. That is what I need to see, all 4 parts. I need your hypotheses, I need to see your test stat and your p-value, and then reject the null or fail to reject the null with its conclusion statement afterwards. Number 2, a simple random sample, use either method. A large software company gives job applicants a test of programming ability, and the mean for the test in the past has been 160. 25 job applications are randomly selected. They produce a mean score of 183, so that's X bar, and a standard deviation of 12, that's S. Use a 0.05 significance level to test the claim, so that's where you start to pay attention, that this sample comes from a population with a mean score greater than 160. So this is the everybody up here. And then this is a sample that we took of 183, and they gave me a standard deviation of 12, but I didn't get the sigma. I know the mean for everybody. I know mu, but I don't know what the sigma is. And if you don't know sigma, it's a t, in this case, test, right? So before we didn't know sigma was a t interval because we were talking about confidence intervals. Now it's going to be a t test since I'm doing a hypothesis test. And I'm going to test the claim that the mu value is actually greater than 160. That's my claim, since my sample data was much higher. The opposite of greater than is less than or equal to, and as soon as you say equal to, you know you have the null. So I have my null hypothesis and my alternate. That's that first part right here where it says give the alternate and the null. Since it's a one-tailed test, all of the error would be put up in the right-hand side. And that's what I would need to identify in order to find this critical t-value. But we're going to go ahead and use a p-value. We're going to go stat over to test, t-test. I have the stats. In the mu naught goes whatever value is in your h naught, which is 160. X bar is a 183. S is 12. I had 25 applications, and then I'm going to match the symbol in this row to whatever is in my alternate, and that is a greater than, so that's the last one. I'll scoot over that, hit enter, and then I'm going to hit calculate, and I have my critical test the test statistic of a 9.58, which is huge. So your test stat is a 9.58. Really big absolute values mean you're probably talking about a 0 for a p-value, and we certainly are here because we know it's not 5. It's actually 0.9 zeros and then the 5, so my p-value is just a 0. And again, I ask myself the question, is the p low? If yes, then reject the null. And in this case, for sure, 0 is less than a 0.05, so once again, I'm going to reject the null. But this time, that's good news. If I chart, I can see that did the original claim contain the equality? No, I said it was greater than. So I'm going to go down to this bottom arrow. Did you reject the null? Yes, I did. Good news. The sample data supports the claim that this sample did come from a population that has a mu value, an overall population mean that's greater than 160. So this time I'm happy. Every once in a while you get to be happy in stats. Doesn't happen too often. There is sufficient sample data to support the claim. The wording matters. 2 more and then we're done. Test the claim. Use whatever method you want. We'll use p-value method again. Identify the same things. The mean resting pulse rate for men is 72 beats per minute. That's pretty accurate. Simple random sample of men who work out at Mitch's gym, is obtained, and we found that their resting pulse rates are these, right? So we said, hey, can we take your pulse? Hey, can we take your pulse? And then we wrote it down. Use a 0.05 significance level to test the claim that the sample pulse rates come from a population with a mean less than 72 beats a minute. Assume that the standard deviation for the resting pulse rates of all men who work out is known to be 6.8. That's important because that's sigma. What we get from in here is just sample data. So that's going to be X bar and S. I want to test the claim that the pulse rates come from a population that is less than 72. That's my claim. The opposite of less than is greater than or equal to, and if you say equal to, you know you have the null. So there's my null and my alternate. I'm going to need to generate a test stat and a p-value, but this time I have all of the data. So instead of running 1 vars almost twice, right, running 1 vars, getting an S and an X bar, and then putting it in, I'm just going to go into stat edit, put in my data, and I'll check it to make sure that it's actually in right. When I hit second mode to go out to the main screen, I'll hit stat, go over to tests. This time I'm going to run a t-test because I don't know, this time I'm going to run a z-test because I do know the population standard deviation. It's 6.8. But I don't have the stats from the data. Remember, stats is for data, parameters for population. I have the actual data, so I'm going to scoot over to data and highlight that, and it will go into L1 and get what you need, your X bar and your S. So now I just have to fill in the rest of this. In my null is a 72. Population standard deviation is 6.8. Skip list, skip frequency. Now we're going to match what's in my alternate, which is a less than, and then I'll hit calculate, and it will take, oh, that was actually much faster than I thought. I have my critical z value, my test stat value, -2, basically right on the dot. So my test stat is a -2. My p-value is 0.0225. I'm going to round to the hundredth, so a 0.02. Is 0.02 less than 0.05? Yes. So then, once again, we're happy. We're going to reject the null. The original claim did not contain the equality. I thought it was less than, so I'm going to say no. Did we reject it? Yes. Good news. Once again, you were right. Sample data supports the claim. Sample data supports the claim. One more, and then we are done. But unfortunately, we're going to have to do this by hand. Use the traditional method because that's all we got. Formula spelled wrong, so I must have typed this up. And chi-squared to test the hypotheses. Assume that the population is normally distributed and the sample is randomly selected. standard deviation of math test scores at a high school is 6.1. Teacher claims that the standard deviation of the girls' test score is smaller than 6.1. Use a random sample of 22 girls. Results and scores with a standard deviation of 12. Use a 0.01 significance level to test the claim. And of course, that claim was that the girls' test scores is smaller than the 16.1. So my claim is that the standard deviation is less than a 16.1. The opposite of less than is greater than or equal to. And if I say equal to, we know that we have our null. So there's my null, there's my H sub 1. Now I'm going to need a test statistic. And since I'm doing this the traditional way, I'm going to need those critical values. It's a one-tailed test. We're only worried about the low end because it's a less than. There's a 0.01 in that area to the left, which leaves a 0.99 to the right, which for chi values is important. So if I have 22 girls in my sample set, DF must be 21. And I need, where do I put up the wall? What chi-value location do I put up the wall that gives me an area to the right of a 0.99? And I have a DF of 21. So I'm going to say from the chi-value chart, area to the right is 0.99 down to the 21, and I get 8.897. That is going to be that critical chi value. So now I need to find my test statistic. My test statistic formula can be found on the formula card. We'll see it here under the chapter 8. Here's chi squared, n minus 1. That's my DF times the standard deviation for the sample squared over the population. Standard deviation squared. Easy enough. Let's go back to the PDF. 21 is my DF. My standard deviation for the girls was 12. Population is a 16.1. And I'm going to find my test stat. 21 times 12 squared divided by a 16.1, that quantity squared. Ooh, and I get an 11.67. And 11.67, if I was going to throw a dart at the map, lands right in here. That is the green zone, right? So if it lands in the big zone, then that's a keep. Or what we say, fail to reject. If it lands in the tail or the red zone, then that's a reject. So this is going to be a fail to reject. I'm going to fail to reject the null. Then I'm going to use my flow chart to see if I'm happy or sad. So back down to the flow chart. Did the original claim contain the equality? No, we said it was less than. Did you reject the null? No, unfortunately I did not. There is not sufficient sample evidence to support the claim. So even though the data set generated values that were smaller, overall that's not true. That does not appear to be true. So there is not sufficient sample evidence to support the claim that girls have a smaller standard deviation than the overall population. That is your overall test. It will be the same length, and you're going to need to make sure that you give all 4 pieces for your hypothesis test.